This is an Algebra 2 class, and today we're going to learn how to solve logarithm equations. We're going to look at several types of logarithm equations, but to start with, we're going to look at equations that only have logarithms with the same base. So if we have an equation that only has logarithms, there's no numbers that's not associated with the logarithms, we're going to start by setting the arguments equal to each other, solve for the variable, and then we always need to check the solution. Remember, the domain of the log function is that it has to be greater than 0, so the argument of the logarithm has to be greater than 0. So let's start with example number 1. In example number 1, we have a log, and they're both to the same base. Since the log base 5 on both sides is the same, the arguments must be equal. So 4x minus 7 must equal x plus 5. Solving that by subtracting x from both sides and then adding 7, we get 3x equals 12. So x is equal to 4. Not quite done yet. We need to check. So we're going back to the check, and it always needs to be checked in the original equation. I don't want to come back here and check it at this stage. It has to work in the original equation for it to be a solution of that equation. So let's put 4 back into our original equation. We have log base 5 of 4 times 4 minus 7. Does that equal log base 5 of 4 plus 5. Simplifying on each side, we have log base 5. We have 16 minus 7, which is 9. And on our other side, 4 plus 5 is equal to 9. These two are the same. This number right here, of which we're doing the logarithm, is positive. So everything is fine. X equals 4 checks. Okay. Sometimes we have an equation that has both logarithm numbers and numbers that are not associated with a logarithm. In that case, we want to make sure that we have the logarithm expression on one side of the equation combined into one logarithm. And we're going to do that if necessary by using the properties of logarithms. Then we're going to take that equation and we're going to convert back to exponential form. We're going to solve the equation, and finally we're going to check the solution in the original equation. So let's start with example number 2 here. On the left side we have a log expression, and on the right side we have just the constant 3. So the log is by itself on one side of the equation. Step number 1 is taken care of. Step number 2 says to convert back to exponential form, so let's do that now. We have a base of 4 raised to the power of 3. So 4 to the power of 3 is equal to 5x minus 1. Well, 4 to the third power is 64, so we have 64 equals 5x minus 1. Add 1 to both sides. 5x is 65. Dividing by 5 gives us x equals 13. And now we're going to check it in the original equation. So we're going to do log base 4 of 5 times 13 minus 1. Does that equal 3? Simplifying, 5 times 13 is 65 minus 1 is 64. And we have, oops, that's not base 5, that's base 4. It's a good thing because it works when it's base 4. We have log base 4 of 64 is equal to 3, and that checks. So our answer checks. Okay, number 3, we have the logs on one side of the equation, but they're not combined into a single log. We have 2 log expressions. So I need to combine those logs into one logarithm using the properties of logarithms. The property that we're going to use here is that the log of m plus the log of n can be combined into the log of m times n. And Notice we don't have a base showing here, so remember that means base 10. So let's take and combine that into one log by taking the 2x times the x minus 5. And now distribute. We're going to have the log of 2x squared minus 10x equals 2. So now I have a single log on one side of the equation. I'm going to move to step 2 and convert back to exponential form. Remember, this is base 10, so I have 10 raised to the power of 2 equals 2x squared minus 10x. Getting one side equal to 0, so let's subtract 10 squared from both sides. We get 0 equals 2x squared minus 10x minus 10 squared, which is 100. All of these terms are even, so a nice first step before solving this quadratic equation would be to divide both sides by 2. And of course, 0 divided by 2 is just 0 on the right, leaving us with x squared minus 5x minus 50 on the right side. So this just happens to factor. If it doesn't factor, you're going to have to use the quadratic formula. But in this case, it does factor, so let's go ahead and do that. Factors at 50 that add to negative 5 would be negative 10 and 5. So I have x minus 10 times x plus 5. Setting each one equal to 0 gives us x equals 10 or x equals negative 5. Now I need to go back and I have to check. Can't leave that check out. So let's go ahead. I've got a little bit of room over here. Let's check number 3 on this side here by putting 10 back into our original equation. Always has to check in the original equation. So this gives us, substituting 10 in for x, log 20 plus log 5 equals 2. Both of these terms are positive, so I can proceed to the next step. If they were negative, it wouldn't check. So we have log 100 equals 2. And yes, that checks because 10 to the second equals 100. So x equals 10 works. Now let's check x equals negative 5 into the original. When I put negative 5 into the original, I get log of negative 10 plus log of negative 10 equals 2. At this point, these two values are negative. It's not defined on values where our argument is negative. So x equals negative 5 does not check. Okay. We can't have the argument of a logarithm less than or equal to 0. So our only solution on this one is x equals 10. Okay, let's move on to another example. Same type. We have two logs here on one side of the equation equal to a constant. So we're first going to combine those using the product, or the sum of two logs becoming a product. So the sum of these two logs becomes the product of the log of base 4 of x plus 12 times x. And that equals 3. Distributing, we get log base 4 of x squared plus 12x equals 3. And now the tricky step, we have to take it out of log form, identify the base, to the power equals the argument. So 4 to the third equals x squared plus 12x. 4 to the third is 64. Again, get one side equal to 0 because it's a quadratic equation. And this also factors. The factors of 64, one positive and one negative that add to 12 are going to be 16 and 4. So we have x minus 4 and x plus 16 equal to 0. So we have two solutions. Either x is 4 or x is negative 16. We need to then check those. So let's check. Substituting 4 in both places in our original equation. Not here, not here, not there, but all the way back in the original equation. So substituting 4 in, we get log base 4 of 16, 4 plus 12, plus log base 4 of 4, and does that equal 3? Well, log of 16 base 4 is 2, log of 4 base 4 is 1, yes, 2 plus 1 equals 3, so x equals 4 checks. Now let's try negative 16. You may be seeing that there's going to be a problem right at the very beginning. When I put negative 16, I end up with log base 4 of negative 4 plus log base 4 of negative 16 equals 3. Can't happen. We can't have a log of a negative, so this one is an extraneous solution. It does not check. Okay, in our last example, we have a single log, but it's not by itself. So we're going to get this single log by itself first by subtracting 3 from both sides. So 4 natural log of negative x is equal to 18. Then we're going to divide both sides by 4. So the natural log of negative x is going to equal 4.5. And we're going to take it out of log form. We take it out of log form. We have to identify the base, and our base in this case is e. So e to the 4.5 equals negative x. Now we're going to go to our calculator, and we're going to find e to the negative 4.5. So second function, ln key gives us e to the power, and we want to take it to the 4.5. So we get 90.02 to the nearest hundredth. So 90.02 equals negative x. To complete this, we need to divide both sides by negative 1, so x is negative 90.02. Now let's check it and see how it works. Again, into the original equation, 4 times the natural log of negative, that becomes positive 90.02. Add 3, does that equal 21? Well, let's check it. Let's do, with our calculator, let's check our left side, see if it works. We have 4 times the natural log of 90.02 plus 3. We did some rounding, so I think we're going to get close to 21, but not quite 21. We got really close, 21.0001. So our answer is going to check. X is negative 90.02. Okay, here's an application of solving logarithm equations. In this case, we have the apparent magnitude of a star, and it's a measure of the brightness of the star as it appears to observers on Earth. So the apparent magnitude, we call that m, of the dimmest star that can be seen by a telescope is given by the equation m equals 5 times the log of d plus 2, where d is the diameter in millimeters of the telescope's objective lens. Okay, so if a telescope can reveal stars with magnitude 12, what's the diameter of its objective lens? So we're going to put 12 in for m into our equation. So I have m equals 5 log of the diameter, then plus 2. So substituting in 12. I need to get the log expression by itself. So I need to subtract 2 from both sides. And I need to divide both sides by 5, giving us 2 equals the log of the diameter, d dot 10. Now taking it out of log form, back to exponential form. Base is 10, understood to be 10. So 10 to the second equals d. So our diameter of the objective lens for a telescope that will allow us to just see a star of magnitude 12 would be 100 millimeters. And that's our lesson on solving log equations.